Oh, that is so fun. Uh, Bonus points to whoever gets that reference. It's one of my favorite heavy metal groups. And so, welcome to Solving Stuff with Sosa. I believe this is episode 5. Think so. And we are doing the circuit analysis workshop, and this is part 2, where we will be doing node analysis. So let's get to it. Okay, so we are going to be looking at this circuit. This circuit has 3 resistors, a 2 ohm resistor, a 20 ohm resistor, and a 3 ohm resistor. It's got 3 power sources, a 12 volt power supply, and 2 current supplies, a 6 amp and an 8 amp. And what we want to find in this circuit is the power that is absorbed by the 20 ohm resistor. Okay, so now we're going to be doing the node analysis of this circuit. Node. It's easier to say than meshes. And so how are we going to do the node analysis for this circuit? Well, first off, we're going to identify the nodes in the circuit. Now, what is a node? A node is going to be a point in the circuit where many things are connected, and these generate branches where the current is going to be divided. And so we're going to identify the node A up here. We're going to identify the node B up here on the top right, and we're going to identify a node C here in the bottom. Now, notice that we've got 2 points here at the bottom, but the points don't have anything connected in the middle, so that is the same node that's going to be called node C. Okay. Now, whenever we're doing node analysis, there's a door creaking in the background. Could that be a ghost? Yes, it's the ghost of Sarah, my daughter, that's opening the only door in the house that creaks while I'm doing this. But I'm going to leave that in because it's fun. So whenever we're doing node analysis, we always have to select a node that's going to be a reference node. Now, why is this important? Because we're going to be doing the following in the node analysis. We're going to be identifying voltages in the node. So we need to know how we're going to measure those voltages and how to identify them as negative or positive. So in this case, we select one of the nodes. It can be any node that we want, is going to be the reference node. For this analysis, this circuit, I'm going to select C as a reference node. Now, what does this mean? This means the following. C is going to be the reference node, so C is going to be the negative point when I measure a voltage. Okay? That means that if I measure a voltage from A to C, or the voltage in A, this is going to be the positive reference, or the positive point. And in B, in this case, B from C, B is going to be the positive reference when I'm measuring voltages between nodes. And the other thing is that when we're talking about a reference node, this is equivalent to saying that this reference node means that if I'm measuring a voltage with regards to that node, this point C is the 0. Okay, is the 0. Remember that when we're talking about potential voltage potential differences, it's a difference between 2 points. So if I'm measuring from A to C, C is going to be the 0 reference, or from B to C, it's going to be the 0 reference. You thought you were going to escape my funky writing, but no, it's still there. So now we've identified the nodes. The other thing is we're also going to identify the meshes. And let's remember what a mesh is and what a loop is. A loop is going to be a closed path within the circuit where current is going to flow, and none of the elements within that path are repeated. A mesh is going to be a loop that contains no additional loops within it. So we're going to identify the meshes in this circuit, and the meshes, we're going to have a mesh number 1 here, and we're going to identify a current that's going to be called I1, and that I'm going to select that one or set that one clockwise. I'm going to identify a mesh 2 with a current that's going to be called I2 that's going to be going counterclockwise. And lastly, a mesh 3 with a current 3 that's going to be going clockwise. Now, setting the currents clockwise or counterclockwise, we can set them however we want. In the end, when we do the analysis, we're going to get signs with regards to the currents. If the sign is negative, it just means it goes the other way around. And so now that we've established the nodes and the currents, we are going to analyze what's happening in the circuit. So let me go to node A. And we're basically going to be using Kirchhoff's current law for this analysis. So looking at node A, we've got a current I2 that's going into the node A. We've got another current I2 that's going in, I1, I'm sorry, is going into node A, I2 is going into node A, and 6 amps are going out. So we've got I2 that's going in, and then we've got I1, but let's represent I1. I1 is the current that's going through the 2 ohm resistor. And so how are we going to represent that current I1 with regards to what's happening with the 2 ohms? We know that by Ohm's law, the current is going to be voltage divided by resistor. So it's going to be the voltage in A, but notice that the current is going from negative to positive. And how am I establishing this negative and positive? With regards to the negative and positive that I referenced with regards to C, which is the reference node. So in this case, VA is going to be the negative voltage divided by 2 ohms. And we have this expression. Now for node B, something similar is going to happen. I2 and I3 are going out and 8 amps are going in. So 8 amps are going in, I2 is going out, and I3 in this case is going to be the current that's going through the 3 ohm resistor. Now notice that in the 3 ohm resistor, the positive is here and the negative is here regarding the reference. So the voltage is going to be positive, which is VB, divided by 3 ohms. And those are going to be the expressions that represent the currents. And now let's look at one of the meshes, which is mesh number 2, and kind of see what's happening there. In mesh number 2, and if we do the Kirchhoff's voltage analysis there, we're going to have that VB minus VA, and I'm just taking this reference because it's the reference that goes that's congruent with the current that I established counterclockwise. VB minus VA is going to be the voltages in these 2 elements. And since the current is entering the negative, it's going to be minus 12 volts, and the voltage in the 20 ohm resistor is going to be 20 I2. Okay? And so the only thing we're doing here is that we're applying Kirchhoff's current law here, and we're doing that with regards to the nodes. And over here, we're applying Kirchhoff's voltage law in one of the meshes. And we could have done it in all of the meshes, but we really don't need to do it in all of them. We just need expressions that relate all of the voltages we have. Now, once we have these, let's try to play around with these and see how we can find the values of the variables that we have there. Wait a minute, where am I? Everything's dark. Oh, wait, no, I'm in Solving Stuff with Sosa, the YouTube videos. I have turned off my camera. Don't worry, I'm still here. Why have I turned off my camera? Because I'm going to be using part of the canvas and I don't want my big face to be interrupting that. So now we've identified the relationships using the Kirchhoff's current law and Kirchhoff's voltage law and doing a node analysis. And so from mesh 2, we had this expression here, which was VB minus VA equals minus 12 volts plus 20 I2. And what we're going to do there is that we're going to we're going to represent that equation with regards to I2. So that gives us VB minus VA plus 12 divided by 20. That's equation 1. We're going to call that equation 1. And now, for node A, we had also an expression that had I2 and VA in this case. We are going to substitute I2. Okay, what we're doing is we're substituting I2 that we just found in equation 1, we are substituting that over here in the node A equation that we had. And once we do that, we're going to work around this and leave the expression with regards to VB and VA And we're going to call that equation 2. The only thing we're doing here is multiplying, in this case, by the factor that we have here, and doing some algebra there to represent this equation. And now from node A, we had this expression here, which was also with regards to I2 and VB. And we are also going to substitute I2 here, the expression we found from equation 1. And what we're going to get is an expression now that has only VB and VA, and we're also going to manipulate some algebra there, and we're going to get this equation that has VA and VB, and that's going to be called equation 3. Okay, so notice now that we've got 3 equations that represent VB and VA, but if we're looking at the voltages, we've got 2 voltages, VB and VA, and so if we've got 2 variables, we only need 2 equations to solve for these variables. So we create a system of 2 by 2, which is going to be using equation 2 and equation 3. And these 2 equations represent VA and VB. Now we have to solve those equations. Now solving those equations is maths, and I'm not going to solve those here because you should already know maths if you're going to be doing this circuit analysis workshop. But I'm giving you a very practical web page there that can help you do the solving of the equations. Ooh, hello everybody. I'm still in the dark, in the unknown. No, not really. I'm here. I just still have my camera off because I need the canvas. And so my camera's still off, but I'm still here. So now that we've got the equations and we've solved them, we find that we've got values for VA and VB. Now, don't worry if any of these values is negative. It just means that the reference is the other way around as to how we had established it, but it's not a problem. So we've got the values for VA and VB. Now, remember that what we're looking for in the end is that we want the power in the 20 ohm resistor, okay? So we don't really need to solve everything in the circuit. We just need enough information to get the power in the 20 ohm resistor. And so we also had an expression that related the current I2 with VB and VA. And so remember that the current I2 is the current that's going through the 20 ohm resistor. So if we substitute these 2 values that we found in VA and VB, if we substitute these into this expression, we can find I2, okay? And so I2 is going to be 1.92 amps. And so having I2 and having, we can also find the voltage in the 20 ohm resistor, and the voltage is going to be the 20 ohms multiplied by 1.92 amps using Ohm's law, and that's going to be 38.4 volts. Now, how do we calculate the power in the 20 ohm resistor? The power is going to be the voltage multiplied by the current. And so the power is going to be the 38.4 volts multiplied by 1.92 amps. That's going to give us 73.728 watts, which is actually the value of the answer, rounded up, of course. And so, yeah, that makes James Hetfield happy. And so, yeah. We've found what we needed to find using node analysis. And so I'm back from the unknown, the dark. My camera's back on. And so I hope you guys, everybody, enjoyed and learned something in this circuit analysis workshop where we were applying node analysis to solve a circuit. So solving stuff with Sosa. Let's make this viral. See ya. Bye.